In 1940, the United States faced a problem that couldn't be solved by courage. It couldn't be solved by strategy. It couldn't even be solved by money. The problem was mathematical and absolute. America needed to build 50,000 aircraft per year. The nation's entire machine tool capacity could build 12,000. Every machine shop in America was already operating at maximum capacity. Building more aircraft required building more machine tools, but building machine tools required machine tools. The circular dependency was unbreakable, unless someone designed machines that could build other machines, machines that could reproduce themselves, machines that could bootstrap an entire industrial revolution in 36 months. This is the story of the engineers who solved the unsolvable problem. They didn't just design better machines. They designed machines that made machine-making possible. They built the machines that built the machines that won the war. Historical context: the machine tool crisis. By 1940, military planners understood the scope of the disaster. Germany had spent 7 years building industrial capacity. The Soviet Union had industrialized at catastrophic human cost. Britain was struggling to replace equipment faster than it was being destroyed. America had superior industrial capacity on paper, but paper capacity and actual capacity were completely different things. The bottleneck wasn't steel or workers or factories. The bottleneck was machine tools. Machine tools are the machines that make other machines. Lathes that shape metal components, milling machines that cut precise surfaces, drill presses that create exact holes, grinding machines that achieve microscopic tolerances. Without machine tools, you cannot build engines. Without engines, you cannot build aircraft. Without aircraft, you cannot win a modern war. The numbers were catastrophic. America had approximately 940,000 machine tools in 1940. This sounds substantial until you understand the requirements. A single B-17 bomber required 450,000 machining operations to produce. Each operation required a machine tool. The math was simple and devastating. Building 50,000 aircraft per year required 22.5 billion machining operations. At current capacity, this would require 24 years. The war wouldn't wait 24 years. The War Production Board issued a stark assessment in March 1941. Machine tool capacity represents the ultimate bottleneck in American production. We cannot build aircraft faster than we can build the tools to build them. The report concluded with an estimate. Expanding capacity to meet requirements would take 8 to 10 years. Germany would control Europe by then. President Roosevelt demanded alternatives. The military demanded miracles. Industry demanded the impossible. What they got was something nobody had considered. Not faster machine tools, not more machine tools, but machines specifically designed to build other machines. The concept violated every principle of industrial design. Machine tools were precision instruments. They required skilled machinists to operate. They took months or years to build. The engineers who solved this problem didn't improve existing designs. They fundamentally reimagined what a machine tool could be. They created devices that could be operated by workers with minimal training. They designed machines that could manufacture identical copies of themselves. The lead engineer on this project was a man named William E. Keller. He worked for Cincinnati Milling Machine Company. He was 34 years old. He had never designed a machine tool before. His lack of experience was his greatest asset. He didn't know what was impossible. So he designed machines that veteran engineers said couldn't exist. The first prototype was completed in August 1941. It was a vertical milling machine that could manufacture its own components. Given raw materials and basic setup, It could produce every part necessary to build another identical machine, except the electric motor, and the control systems, and about 40 specialized components, but everything else, the frame, the bed, the table, the column, the spindle, could be manufactured by the machine itself. The self-replication rate was approximately 73%. Traditional machine tools had a self-replication rate of about 15%. The improvement was nearly five-fold. The military evaluated the prototype in September 1941. The test was simple. Use the machine to build components for another identical machine. The machine operated continuously for 96 hours. It produced 94% of the required components within specified tolerances. The evaluators were stunned. General Levin Campbell wrote, "This device represents a breakthrough comparable to the invention of interchangeable parts. It is not merely a better machine tool. It is a machine tool that propagates industrial capacity." The Army ordered 2,000 units immediately. Then someone asked the obvious question, how do you build 2,000 machines when you only have one prototype? The answer was elegant. You use the first machine to build components for 2 more machines. Then you use those 3 machines to build components for 6 more machines. Then you use those 9 machines to build components for 18 more machines. Exponential growth, geometric expansion, industrial mitosis. By December 1941, the theory was proven. By March 1942, production reached 40 machines per month. By December 1942, production reached 340 machines per month. The machines were building themselves faster than engineers could design new variations. Technical analysis, engineering self-replication. The core challenge was eliminating specialized components. Traditional machine tools used dozens of custom parts. Each custom part required specialized manufacturing. Specialized manufacturing required specialized tools. Keller's approach was ruthlessly pragmatic. Eliminate anything that requires specialized production. Redesign everything to use standardized components. Accept reduced precision in exchange for reproducibility. The frame was the first breakthrough. Traditional machine tool frames were cast iron. Casting required patterns, molds, foundries, and weeks of curing time. Each casting was unique and required individual finishing. Keller's frame was welded steel, standard steel plates, standard dimensions, standard welding procedures. Any competent welder could fabricate a frame in 14 hours. The frames were heavier than cast iron equivalents, but far faster to produce. The weight penalty was 340 pounds per machine. The time savings was 6 weeks per machine. The trade was obvious. The bed was the next challenge. Traditional machine beds were precision ground cast iron surfaces. Grinding to the required tolerances took 40 hours per bed. It required skilled operators and specialized grinding machines. Keller used hardened steel plate bolted to the frame. The plate was ground at the steel mill, not at the assembly facility. This shifted the precision work upstream to specialized facilities. The final assembly required no precision grinding at all. The tolerances were looser, 0.002 inches instead of 0.005 inches, but for 80% of machining operations, the difference was irrelevant, and the production time dropped from 40 hours to 6 hours. The spindle design was revolutionary. Traditional spindles used tapered roller bearings with micron-level tolerances. These bearings were imported from Sweden or Switzerland. The supply chain was fragile and slow. Keller designed a spindle using standard ball bearings. The bearings were less precise, but far more available. The design compensated for bearing imprecision through mechanical advantage. The result was 85% of the precision at 15% of the cost and 5% of the delivery time. The drive system eliminated custom gearing. Traditional machines used precision-cut gears for speed control. Keller used V-belt systems with standardized pulleys. The speed control was less precise, but far simpler to manufacture. Every design decision followed the same logic: standard components instead of custom parts, simplified manufacturing instead of maximum precision, reproducibility instead of optimization. The result was a machine that could be built by other machines with minimal specialized tooling. The self-replication cycle worked like this. Machine A manufactures the frame components for machines B and C. While machine A is cutting frame components, it also manufactures bed plates. The bed plates require 14 hours of continuous machining per plate. Meanwhile, standard components, motors, bearings, pulleys, belts, arrive from suppliers. These suppliers aren't making custom parts. They're producing standardized industrial components in massive quantities. The assembly process was designed for speed, no precision fitting, no hand scraping of bearing surfaces, no custom adjustments. Everything either bolted together or it didn't. If it didn't bolt together, the component was out of tolerance and rejected. But the rejection rate was only 3.2%. The assembly time was 47 hours from components to operational machine. This included setup, testing, and calibration. Traditional machine tool assembly took 300 to 400 hours. The machines weren't as precise as traditional tools. They weren't as durable. They weren't as versatile. But they could be built in 1/8 the time, at 1/3 the cost, by workers with 1/10 the training, and, most importantly, they could build copies of themselves. The production mathematics were extraordinary. Start with 10 machines in January. Use them to build components for 20 machines by March. Use those 30 machines to build components for 60 machines by May. By December, theoretical capacity was 20,480 machines. Actual production was limited by component suppliers and assembly facilities, not by machining capacity. The bottleneck had shifted. The geometric expansion created a new problem. The machines were producing components faster than they could be assembled into finished machines. Warehouses filled with machine beds, frames, spindles, and tables waiting for assembly. The solution was obvious: design machines that could build assembly fixtures. The assembly fixtures would speed up the assembly process, which would allow more machines to be completed, which would produce more components, which would require more assembly fixtures. The cycle became self-reinforcing. By mid-1943, the machine tool shortage had been solved. The limiting factor was no longer machine tools. It was skilled labor to operate them. So Keller designed machines that didn't require skilled labor. Semi-automatic revolution, machines for untrained operators. The second-generation design emerged in November 1942. These machines incorporated automatic feeds and mechanical stops. The operator didn't control the cutting operation. The machine did. The operator's job was reduced to 3 tasks: load the workpiece, press the start button, remove the finished part. Everything else was automated through mechanical systems. Cams controlled the cutting depth. Mechanical stops controlled the travel distance. Spring-loaded returns repositioned the cutting head. No skill required, no judgment calls, no experience necessary. The training time dropped from 6 weeks to 6 days. The error rate dropped from 8% to 1.2%. The production rate increased by 40%. The machines were slower than manually operated versions, but the operator could supervise 3 machines simultaneously. The net result was 210% productivity improvement. The semi-automatic machines created a new category of worker: not machinists, not laborers, something in between. The job title was machine tender. No previous experience required. High school education sufficient. Training provided on site. Women filled 78% of these positions. Teenagers filled another 15%. Men over 50 filled most of the remainder. These were people who would never have been considered for precision manufacturing in peacetime, but wartime had no room for peacetime prejudices. If you could follow instructions and maintain focus, you could operate a semi-automatic machine. Martha Reynolds was 19 years old when she became a machine tender. She had worked as a grocery store clerk. Her technical training consisted of 2 days of instruction. By the third day, she was operating 3 machines simultaneously. Her job was producing engine-mounting brackets for B-24 bombers. Each bracket required 14 separate machining operations. The semi-automatic machines performed all 14 operations with one setup. Martha loaded raw castings into Machine 1, Machine 2, and Machine 3. She pressed 3 start buttons. 17 minutes later, she removed 3 finished brackets and loaded 3 more castings. She produced 47 brackets per 8-hour shift. A skilled machinist on traditional equipment produced 12 brackets per shift. Martha was 4 times more productive despite having 1/50th the training. The economic implications were staggering. Martha earned 0.85 per hour. A skilled machinist earned $1.80 per hour. Her per-unit labor cost was 18 cents per bracket. The skilled machinist's per-unit labor cost was 72 cents per bracket. Multiply this across thousands of workers and millions of parts. The cost savings funded more machines, more factories, more production. But the real breakthrough wasn't efficiency. It was scalability. Finding 10,000 skilled machinists was impossible. Finding 10,000 people who could load parts and press buttons was trivial. The semi-automatic machines transformed manufacturing from an artisan craft into an industrial process. The training process itself was revolutionary. Traditional machinist training took 4 years of apprenticeship. The apprenticeship covered blueprint reading, material properties, cutting speeds, tool selection, measurement techniques, and machine operation. A journeyman machinist understood why each operation was performed. Machine tenders needed none of this knowledge. They didn't need to read blueprints. The machine was set up for them. They didn't need to understand material properties. The cutting parameters were preset. They didn't need to select tools. The tools were already mounted. They needed to understand 3 things: load the part in the fixture correctly, recognize when the cycle had completed, identify obviously defective parts. Day 1 of training covered part loading. The fixture was designed to accept parts in only one orientation. If the part didn't fit easily, it was oriented incorrectly. This eliminated a major source of errors. Day 2 covered cycle recognition. The machine made specific sounds during operation. A buzzer indicated cycle completion. A red light indicated a jam or malfunction. Green light, machine operating correctly. Red light, call the supervisor. Day 3 covered defect identification. Trainees were shown examples of good parts and bad parts. Good parts, smooth surfaces, no burrs, correct dimensions. Bad parts, rough surfaces, visible burrs, obvious dimensional errors. The training emphasized, when in doubt, call the inspector. Days 4 through 6 were supervised operation. Trainees operated machines under direct supervision. Supervisors caught errors before they became problems. By day 6, most trainees could operate independently. The simplicity was deliberate. The machines were designed to make operator errors nearly impossible. The fixtures ensured correct part orientation. The automatic cycles ensured correct machining operations. The final inspection caught the few defects that occurred. Helen Kowalski was a training supervisor at a Detroit aircraft plant. Her job was teaching machine tender skills to new workers. She trained over 2,400 workers during her 3 years in the role. She described the biggest challenge. People expected the job to be complicated. They were intimidated by the machines. My job was showing them that the machine does the complicated work. They just feed the machine. Her training technique was simple. Demonstrate once, assist once, observe once. On day 1, she demonstrated proper part loading 3 times. Then she had the trainee load a part with her assistants. Then she had the trainee load 3 parts while she observed. If the trainee could load 3 parts correctly, they understood the process. If they struggled, she demonstrated again. She never moved to day 2 until day 1 was mastered. Her success rate was 97.8%. Of the 2,400 workers she trained, 2,347 completed the program and became productive machine tenders. The 53 who didn't complete the program weren't failures. They were reassignments. Some couldn't handle the repetitive nature, some couldn't maintain focus for 8-hour shifts. They were moved to different roles better suited to their capabilities, but 97.8% could do the job. This was the genius of the semi-automatic design. The machines were designed for nearly universal human capability. If you could follow simple instructions, you could operate the machine. The age range of successful operators was astonishing. The youngest machine tender on record was 16 years old. The oldest was 71. Both achieved production quotas consistently. The 16-year-old was Thomas Sullivan, working at a Long Island aircraft plant. He had lied about his age to get the job. He was actually 15. When his real age was discovered, management faced a dilemma. Child labour laws prohibited factory work for minors, but Thomas was one of their best machine tenders. 0 defects over 6 months of work, never missed a shift, never had a safety incident. The plant manager petitioned the State Labour Board for an exemption. The exemption was granted with conditions: limited hours, mandatory supervision, no hazardous operations. Thomas worked 6-hour shifts instead of 8-hour shifts. He graduated high school while working part-time in aircraft production. The 71-year-old was Heinrich Schmidt, a German immigrant working in a Cleveland engine plant. He had been a toolmaker in Germany before emigrating in 1923. He had retired from toolmaking in 1938 at age 67. When war began, he volunteered to return to work. The plant initially tried to utilize his toolmaking skills, but his hands shook too much for precision work. He was reassigned to machine tending. His experience as a toolmaker made him exceptionally good at identifying defects. His defect detection rate was 99.94%, better than most inspectors. He worked until his death in 1945 at age 73. He collapsed at his machine station during a shift. The plant held a memorial service attended by 400 workers. These stories illustrate the social revolution enabled by semi-automatic machinery. People excluded from precision manufacturing by age, gender, or lack of training could now participate productively. The machines democratized industrial participation. By 1943, semi-automatic machine tools outnumbered traditional machines in aircraft production facilities. By 1944, the ratio was 3-to-1. The machines had democratized precision manufacturing. The social resistance to this change was significant. Traditional machinists saw their skills being devalued. Unions worried about wage compression. Factory managers worried about quality. The United Auto Workers Union initially opposed semi-automatic machinery. They argued it would eliminate skilled jobs. They demanded that only journeyman machinists be allowed to operate the new machines. The War Labour Board rejected these demands. The board's ruling was blunt. The nation's security cannot be subordinated to craft preservation. Semi-automatic machinery enables production volumes that cannot be achieved through traditional methods. Opposition to these tools is opposition to victory. The ruling was harsh but necessary. Without semi-automatic machinery, production targets were unachievable. The skilled machinist workforce was insufficient and couldn't be expanded quickly enough. But the unions had a legitimate concern. What would happen to skilled machinists after the war? If semi-automatic machines could replace them, would they have jobs? The answer turned out to be surprising. Skilled machinists became more valuable, not less valuable. Semi-automatic machines handled routine production operations. This freed skilled machinists to focus on setup, troubleshooting, prototype development, and quality inspection. The machinists became supervisors and specialists. Their expertise was leveraged across multiple machines and operators. Instead of personally producing 12 brackets per shift, they oversaw systems producing 500 brackets per shift. Their wages increased, their responsibility increased, their skills became more valuable because they were scarcer relative to production volume. By 1945, skilled machinists earned 40% more than they had earned in 1941. The semi-automatic revolution had increased their value. Thomas Warner was a journeyman machinist who transitioned to production supervisor. He oversaw 12 semi-automatic machines operated by 4 machine tenders. His job was setup, maintenance coordination, and quality verification. He wrote to his brother in 1944, "I thought these automatic machines would put me out of work. Instead, I'm earning more than ever, and my skills are more valuable. The machines do the routine work. I do the thinking. Turns out thinking is worth more than turning handles." The economic transformation was profound. Labour productivity increased by 340% between 1941 and 1944. This wasn't because workers worked harder. It was because machinery amplified their capability. One person operating 3 semi-automatic machines produced more than 3 skilled machinists on traditional equipment. The multiplication of human capability through machinery was the core advantage. Germany never achieved this transformation. German factories continued using highly skilled craftsmen on traditional equipment. German machinists produced superior individual parts, but they couldn't produce sufficient volume. A German machinist might produce a component to 0.001 inch tolerance. An American machine tender might produce a component to 0.112 inch tolerance. The German component was higher quality. But the American factory produced 50 components for every German component. 49 of those American components worked perfectly fine. Quantity overwhelmed quality. This was the lesson of semi-automatic machinery. Perfect is the enemy of good enough. Good enough, produced in quantity, wins. Perfect, produced in limited numbers, loses. Transfer machines, the ultimate automation. The third-generation design emerged in 1943. These were called transfer machines. The name described their function. They transferred workpieces between stations automatically. A transfer machine was essentially 12 machine tools connected in sequence. The workpiece entered at station 1. It progressed through all 12 stations automatically. It emerged as a finished part. The operator loaded raw parts at the beginning. The operator removed finished parts at the end. Everything in between was automatic. One operator could supervise a transfer machine performing 12 operations. This replaced 12 operators on 12 separate machines. The efficiency gain was approximately 900%. The design was mechanically complex, but conceptually simple. Each station performed one operation. When the operation completed, a mechanical transfer system moved the workpiece to the next station. The system required no electrical controls or feedback mechanisms. Everything was mechanical: cams, levers, springs, and timing chains. If something broke, any mechanic could diagnose and repair it. No specialized electronics training required. The first transfer machine was designed for engine cylinder head production. The cylinder head was one of the most complex components in an aircraft engine. It required 37 separate machining operations. On traditional equipment, this required 37 different setups across multiple machines. The setup time alone consumed 3 hours per cylinder head. The actual machining time was 2.5 hours. Total time per cylinder head, 5.5 hours. A skilled machinist could produce 1.5 cylinder heads per 8-hour shift. The transfer machine changed everything. Loading time, 45 seconds. Machining time, 6.8 minutes. Unloading time, 30 seconds. Total time per cylinder head, 8.1 minutes. That's a 40-fold improvement in cycle time. But the comparison understates the advantage. The traditional approach required a skilled machinist's continuous attention. The transfer machine required operator attention for 75 seconds per cycle. The remaining 6.8 minutes was unattended operation. One operator could supervise 4 transfer machines simultaneously. Each machine produced 7.4 cylinder heads per hour. 4 machines produced 29.6 cylinder heads per hour. One operator was producing what would have required 20 skilled machinists. The design required solving unprecedented engineering challenges. The workpiece had to be transferred between stations without losing positional accuracy. Each station had to know when the previous station had completed its operation. The entire system had to remain synchronized, despite mechanical variations. The transfer mechanism was a mechanical marvel. It used a walking beam system, a rigid bar that lifted all workpieces simultaneously, moved them forward one station, and lowered them into position. The movement was powered by a mechanical cam system driven by the main drive shaft. When Station 1 completed its operation, it triggered a mechanical latch. When all 12 latches were triggered, the walking beam activated. The timing was precise to within 0.3 seconds across all 12 stations. This was achieved entirely through mechanical engineering. No electronics, no computers, no feedback loops, just cams, gears, springs, and very careful design. The system was self-correcting for minor variations. If a station took slightly longer than expected, spring-loaded buffers absorbed the timing difference. If a station jammed, a mechanical overload system stopped the entire machine. The operator could identify the problem station by visual inspection. It would be the only station that hadn't completed its cycle. The reliability was remarkable given the mechanical complexity. Early prototypes achieved 82% uptime. Production models achieved 94% uptime. The improvement came from exhaustive testing and iterative refinement. Every failure mode was documented. Every failure mode was addressed through design changes. By the time production began, the machines were extraordinarily reliable. The transfer machines were built using the same philosophy as the first-generation machines: standard components, simple assembly, reproducible design, and, crucially, transfer machines could manufacture components for other transfer machines. The self-replication principle had been applied at a higher level of automation. The frame was welded steel using standard structural shapes. The walking beam was machined from standard steel bar stock. The stations used standard milling and drilling heads. The drive system used standard electric motors and reduction gears. The only custom components were the cams and fixtures. But these were designed to be manufactured on other transfer machines. A transfer machine producing engine components could, with different fixtures, produce transfer machine components. The bootstrap cycle extended to the highest level of automation. The production rates were extraordinary. A transfer machine producing engine cylinder heads could complete one head every 7.5 minutes. That's 64 cylinder heads per 8-hour shift. A skilled machinist on traditional equipment produced 3 cylinder heads per shift. The transfer machine replaced 21 skilled machinists with 1 machine tender. The capital cost was $47,000 per transfer machine. The annual labor savings was $63,000. The payback period was 9 months. The calculation that made transfer machines economically viable, 21 machinists, x 180 per hour, x 2,080 hours per year, decart 78,624 in annual labor costs. 1 machine tender, x 085 per hour, x 2,080 hours per year, which is 1,768 hours in annual labor costs. Annual savings, 76,850 silang. Maintenance costs approximately $12,000 per year. Depreciation approximately $4,700 per year. Net annual savings $60,156. Even accounting for downtime and operational costs, the transfer machine paid for itself in less than a year. After that, it represented pure productivity gain. By mid-1944, transfer machines were producing approximately 60% of all aircraft engine components. The engines being built in 1944 were mechanically identical to engines built in 1941, but the labour required to build them had dropped by 73%. This wasn't just about saving money, it was about producing volume that would have been impossible with traditional methods. In 1941, American factories produced 19,433 aircraft engines. In 1944, American factories produced 256,911 aircraft engines. That's a 13-fold increase. The workforce grew by only 340%. The difference was machinery. Machines that built engines. The Ford Motor Company's Willow Run plant illustrated the concept at maximum scale. Willow Run produced B-24 Liberator bombers. At peak production, the plant completed 1 aircraft every 63 minutes. The plant employed 42,000 workers. Traditional aircraft production methods required approximately 200,000 labour hours per aircraft. At that rate, 42,000 workers would produce approximately 4 aircraft per week. Willow Run produced 28 aircraft per week. The difference was machinery. The plant contained 1,847 transfer machines and semi-automatic machine tools. These machines performed 87% of all machining operations. Workers performed final assembly, inspection, and quality control. Henry Ford II described the philosophy, "We're not building aircraft. We're building a system that builds aircraft. The system is the product. The aircraft are the output." This distinction was crucial. Traditional aircraft manufacturers focused on building better aircraft. Ford focused on building better aircraft building systems. The aircraft Ford produced weren't superior to aircraft built by traditional methods. They were adequate, but Ford produced them in quantities that traditional methods couldn't match. The Battle of the Atlantic was decided partially by B-24 Liberators. These aircraft provided long-range submarine detection. They closed the Atlantic Gap, where U-boats had operated with impunity. By 1943, B-24 coverage made U-boat operations suicidally dangerous. The U-boat threat collapsed. Allied shipping losses dropped by 87%. Willow Run alone produced 8,685 B-24 aircraft. That's 45% of all B-24s built. Most of the machining was performed by transfer machines. The transfer machines were built by other machines. Those machines were built following Keller's designs. The cascade of capacity enabled victory in the Atlantic. The German response was to focus on superior individual aircraft. The Focke-Wulf FW-190 was arguably the best fighter aircraft of the war. German factories produced 20,051 FW190s over 5 years. American factories produced 15,683 P51 Mustangs over 3 years. The P51 wasn't superior to the FW190, it was roughly equivalent, but the United States also produced 12,031 P47 Thunderbolts, 9,923 P38 Lightnings, 15,386 F6F Hellcats, 12,571 F4U Corsairs. Total American fighter production exceeded German production by a factor of 3. The quality difference was marginal. The quantity difference was decisive. This quantity was enabled by transfer machines and semi-automatic tools. German factories relied on skilled craftsmen using traditional equipment. The German aircraft were masterpieces of precision engineering, but there weren't enough of them. Quality without quantity is insufficient. Quantity with adequate quality wins. The transfer machines represented the ultimate expression of this philosophy. They produced adequate quality at overwhelming quantity. That was enough to win. Logistics of machine production, coordinating the cascade. The machine tool industry faced a unique challenge. Their products were being used to expand their own production capacity. Every machine they built increased their ability to build more machines, but it also increased demand for their products. The production planning was extraordinarily complex. Build too many machines and you exhaust your component suppliers. Build too few machines and you cannot meet aircraft production targets. The War Production Board created a dedicated machine tool allocation committee. This committee met weekly to coordinate machine tool distribution. They tracked machine tool production, machine tool allocation, machine tool utilization, and bottleneck identification. The allocation system prioritized self-replication. New machines went first to facilities that could build more machines. Only after machine building capacity was satisfied did machines go to aircraft production. This delayed aircraft production in the short term, but it maximized aircraft production in the long term. The committee calculated that dedicating the first 6 months of production to machine building would triple eventual aircraft production. The decision was controversial. Army Air Force commanders wanted machines immediately. The committee held firm, build machine capacity first, build aircraft second. The strategy proved correct. By allocating early production to machine building, the cascade effect amplified total capacity. The temporary sacrifice of 6 months of aircraft production enabled an increase that more than compensated within 18 months. The component supply chain was equally critical. Electric motors, bearings, belts, switches, these couldn't be self-replicated. They came from specialized suppliers. The War Production Board tracked 47 critical machine tool components. If any component fell below 60 days inventory, production was prioritized. The system prevented component shortages from halting machine tool production. The coordination extended internationally. Britain needed machine tools desperately. But shipping machine tools across the Atlantic consumed cargo space that could carry aircraft or tanks. The solution was elegant: ship the plans, not the machines. British factories built Keller design machines under license. The machines were designed to be reproducible. They could be built anywhere with basic industrial capacity. By 1944, British factories had produced 4,200 Keller design machines. These machines built components for Spitfires, Hurricanes, and Lancaster bombers. The same design philosophy that enabled American production enabled British production. The Soviet Union requested similar technical assistance. The Keller designs were provided under Lend-Lease. Soviet factories built approximately 7,800 machines based on American designs. These machines built components for T-34 tanks and IL-2 ground attack aircraft. The German response was illuminating. German intelligence obtained Keller design blueprints through espionage in 1943. German engineers analyzed the designs and dismissed them as crude and imprecise. They were right. The Keller machines were crude compared to German machine tools. German tools were masterpieces of precision engineering, but German tools took 6 months to build. Keller machines took 6 weeks to build. Crude and abundant beats, precise and rare. Human impact, the engineers behind the revolution. William Keller didn't work alone. His team included 23 engineers, most under 30 years old. They worked 16-hour days, 7 days per week. The pace was unsustainable, but the timeline was non-negotiable. The design process was iterative and brutal. Design a component, build a prototype, test it, it fails, redesign it, test again, it fails differently, redesign again. The failures weren't weaknesses, they were progress. Each failure eliminated one approach and suggested alternatives. The team celebrated failures as much as successes. Robert Morrison was the lead mechanical engineer. He designed the automatic feed mechanisms for the semi-automatic machines. He submitted 47 different designs before finding one that worked reliably. His notebook from this period survives. It contains 312 pages of sketches, calculations, and notes. On page 187 he wrote, "Failure nur 31, cam timing too aggressive, parts jam every 14th cycle, try softer spring return." On page 188, failure under 32, softer spring too slow. Cycle time increases 40%, try dual rate spring. On page 189, success, dual rate spring with offset cam, testing 1,000 cycles, no failures so far. That design became standard on 12,000 machines. It was the result of 32 failures and 7 months of iteration. The dual-rate spring design was elegant in its simplicity. The spring provided strong force during the initial return movement. As the mechanism approached its rest position, the spring rate decreased. This prevented bounce while maintaining fast cycle times. The design required no adjustment, no maintenance, and no operator intervention. It worked reliably for 2,000+ hours of operation. Then it wore out and was replaced. The replacement cost was £1.40. The design had no single point of failure. If the spring broke, the machine simply stopped. It didn't damage itself. This was deliberate design philosophy. Failures should be obvious and safe. Morrison's design principles were documented in a memo dated March 1943. Design for failure modes that are obvious, safe, and cheap to repair. Never design systems where failure causes secondary damage. The machine should stop cleanly, not destroy itself. These principles became standard across all machine tool designs. The result was machines that rarely failed catastrophically. When they did fail, repairs were quick and inexpensive. The engineering team had no precedent to follow. Machines that build machines didn't exist. They were inventing a new category of industrial equipment. The pressure was immense. Every week of delay meant fewer aircraft built. Fewer aircraft meant more Allied casualties. The engineers felt the weight of that responsibility. James Patterson was a stress analysis engineer. His job was calculating whether components would fail under operational loads. He worked with slide rules and calculation tables. Computers didn't exist yet. Each stress calculation took approximately 45 minutes. A single machine component might require 30 different stress calculations. He performed over 8,000 calculations during the design phase. He made an error on calculation number 1247. The error resulted in an undersized bearing mount. The bearing failed during testing after 47 hours of operation. James discovered his error while reviewing his work. He reported it immediately. The design was corrected before production began. He wrote in his journal, "I nearly caused a disaster that would have delayed production by 3 months. The responsibility is crushing, but catching the error before production, that's why we test." The testing phase was exhaustive. Every machine ran continuously for 500 hours before approval. Failures were analysed, causes identified, designs modified. The target was 99% uptime over 2,000 hours of operation. The first designs achieved 87% uptime. Iteration by iteration, the reliability improved. The production designs achieved 97% uptime. Close enough. Perfect was the enemy of good enough. Good enough won the war. Eleanor Hoffman was the only woman on the engineering team. She held a degree in mechanical engineering from MIT, one of only 14 women who graduated from MIT's engineering program in the 1930s. She joined Keller's team in August 1941. Her specialty was vibration analysis. High-speed machining creates vibrations that can destroy precision. Eleanor's job was designing systems that dampened these vibrations without adding excessive weight. She developed a vibration dampening system using layers of different materials: steel plates for rigidity, rubber layers for vibration absorption, cork layers for high-frequency dampening. The layered system reduced vibration by 73% while adding only 40 pounds to machine weight. The design became standard on all high-speed operations. Eleanor faced skepticism from some team members initially. One engineer told her directly, "Women don't understand machinery." Her response was to calculate the resonant frequencies of his failed design and show him why it had failed. She was never questioned again. Keller wrote in her performance review, "Eleanor Hoffman possesses the finest intuitive understanding of mechanical systems I have encountered in 15 years of engineering. Her contributions have been essential to project success." She worked on the project until August 1943. Then she left to join the Manhattan Project. Her work there remains classified. She never discussed it, even decades later. The engineering team received little public recognition. Keller's name appeared in technical journals, but not newspapers. The machine tools weren't glamorous like aircraft or tanks. They were invisible infrastructure. But the engineers understood their impact. Every aircraft built used components made on their machines. Every tank, every ship, every weapon. Their machines built the tools that built the arsenal of democracy. In December 1945, Keller received the Presidential Medal for Merit. The citation read, "For exceptionally meritorious conduct in the performance of outstanding services to the United States in the design of machine tools that enabled unprecedented expansion of industrial capacity." Keller kept the medal in a drawer. He rarely spoke about his wartime work. When asked, he deflected. "I just designed some machine tools. Other people built them and used them. They did the real work." But his team knew better. Without those machine tools, American production would have been impossible. Without American production, the war would have been unwinnable. Robert Morrison said it best, "We didn't win the war with our machines, but we built the machines that built the machines that gave us the capacity to win. That's enough." The personal cost was significant. Morrison suffered a nervous breakdown in November 1943. He was hospitalized for 6 weeks. He returned to work in January 1944, but never fully recovered his previous stamina. The pressure of knowing that design failures could cost lives was crushing. Every calculation had to be correct. Every design had to work reliably. There was no margin for error. Patterson developed an ulcer that required surgery. 3 engineers left the project due to exhaustion. One engineer, David Foster, died of a heart attack at his drafting table in March 1944. He was 36 years old. The project took everything these engineers could give. Some gave more than they could afford. They gave it anyway because the alternative was defeat. After the war, the teams scattered. Morrison taught engineering at MIT. Patterson joined General Electric's turbine division. Eleanor Hoffman's post-war career is partially documented. She worked at Los Alamos until 1958, then disappeared from public records. Keller returned to agricultural equipment design. He designed a revolutionary combine harvester in 1953. The harvester used many of the same principles as his machine tools: standardized components, simple assembly, operator-friendly design. It became the best-selling combine of the 1950s. He never mentioned that the design principles came from his wartime work. He simply said, "Good design is good design, regardless of application." In 1977, at age 70, he gave a rare interview to an engineering magazine. The interviewer asked, "What are you most proud of in your career?" Keller paused for a long moment. Then he replied, "The machines that made it possible for ordinary people to do extraordinary things. That's what engineering should do. Not make things complicated, but make complicated things simple." He died in 1983. His obituary mentioned his agricultural equipment patents. It mentioned his community service. It devoted one sentence to his wartime work. But that one sentence changed the world. Modern relevance. Lessons in bootstrap industrialization. The Keller machines demonstrated a principle that remains relevant today. Industrial capacity is not static. It can be amplified through self-replication. The key is designing systems that can reproduce themselves. This principle appears in modern manufacturing as modular production systems, factories that can reconfigure themselves for different products, 3D printers that can print components for other 3D printers, automated assembly systems that can build copies of themselves. The underlying logic is identical to Keller's approach: eliminate specialized components, maximize use of standard parts, design for reproducibility over optimization. The Chinese manufacturing industry has applied this principle at national scale. They didn't try to match Western manufacturing quality immediately. Instead, they built good enough capacity at massive scale. Then they used that capacity to build better capacity. The progression is obvious. Chinese factories in the 1990s produced low-quality goods, but they produced them in enormous quantities. The revenue funded better equipment. Better equipment enabled higher quality. Higher quality enabled higher margins. Higher margins funded even better equipment. By 2010, Chinese manufacturing quality matched Western standards. By 2020, Chinese manufacturing capacity exceeded the rest of the world combined. The strategy was identical to Keller's strategy. Build crude capacity quickly, use crude capacity to build better capacity. Iterate until you achieve desired quality. The Western response was to focus on maintaining quality advantages. This preserved margins in the short term, but it ceded volume in the long term. Volume eventually enables quality. The lesson is uncomfortable. In industrial competition, quantity often becomes quality. The side that can produce more will eventually produce better. The side that focuses on producing better may never achieve sufficient volume. The modern semiconductor industry illustrates this perfectly. Taiwan Semiconductor Manufacturing Company, TSMC, dominates chip production, not because they invented the best chip-making technology, but because they achieved the capacity to produce chips at scale. That capacity enabled investment in better technology. Better technology enabled more capacity. The cycle became self-reinforcing. Competitors who focused on perfect technology couldn't achieve sufficient volume to fund further development. TSMC achieved sufficient volume to fund continuous improvement. Now they're both the largest and the most advanced. The same principle applies to artificial intelligence infrastructure. The companies with the most compute capacity can train the best models. Better models generate more revenue. More revenue funds more compute capacity. The bootstrap cycle advantages whoever achieves initial scale. Initial scale requires designs that prioritize reproducibility over perfection. Keller understood this in 1941. Modern industrial strategists are relearning it today. The national security implications are significant. The United States defeated Germany and Japan partially through industrial capacity. That capacity was enabled by machine tools that could replicate themselves. Modern industrial competition follows the same logic. Can the United States bootstrap production capacity in a crisis? The answer is uncertain. The regulatory environment is more complex than in 1940. The skilled workforce is less available. The industrial supply chains are more globalized and fragile. China demonstrates capacity for rapid industrial scaling. They built COVID hospitals in days. They dominate solar panel production. They produce more ships in a month than the US produces in a year. Whether this translates to military production capacity remains untested. But the parallels to 1940s America are obvious and concerning. The lesson from Keller's machines is simple. The nation that can bootstrap industrial capacity fastest will win the next industrial competition. Speed matters more than perfection. Volume matters more than unit quality. Reproducibility matters more than optimization. These principles won World War II. They will determine who wins the next industrial competition. The machines that build machines are the foundation of everything else. Conclusion: the invisible victory. The machine tool industry built 2.3 million machines during World War II. This represented a 10-fold increase over pre-war production. Most of these machines were built using designs pioneered by Keller's team. The machines weren't elegant. They weren't precise by peacetime standards. They weren't built to last decades. But they worked. They could be built quickly. They could be operated by minimally trained workers. And, crucially, they could build copies of themselves. The total cost of the machine tool program was $4.2 billion. That's approximately $68 billion in 2025 dollars. It was one of the largest industrial investments of the war. The return on investment was incalculable. Those machines built 300,000 aircraft. They built 89,000 tanks. They built 3,000 naval vessels. They built 41 million artillery shells. Every weapon, every vehicle, every component passed through machines built by other machines. The cascade of capacity enabled everything else. William Keller returned to civilian engineering in 1946. He never designed another machine tool. He spent 30 years designing agricultural equipment. He retired in 1976 and died in 1983. His obituary in the New York Times was 4 paragraphs long. It mentioned his agricultural equipment patents. It mentioned his community service. It devoted 1 sentence to his wartime work. During World War II, he contributed to defense manufacturing efforts. No mention of the machines that built machines. No mention of bootstrap industrialization. No mention of enabling the arsenal of democracy. Robert Morrison taught mechanical engineering at MIT for 40 years. He occasionally lectured on machine tool design. He never mentioned his wartime work unless directly asked. When asked, he was dismissive. We just made some production equipment, nothing revolutionary, just practical engineering for practical problems. But his students who studied wartime industrial history recognized the significance. One student asked, "Professor Morrison, did you work on the self-replicating machine tool project?" Morrison paused, then replied, "Yes, I designed the feed mechanisms. Why do you ask?" because that project is one of the most important engineering achievements of the 20th century. It enabled the entire American production advantage. Morrison smiled. It was just machine tools. They're not glamorous. Nobody remembers the tools, only what the tools built. The student persisted. But without the tools, nothing else would have been built. Morrison nodded. Exactly, which is why we built them first. Tools before products. Capacity before output. That's the secret nobody talks about. The machines that built machines represent the invisible foundation of modern industrial society. Every factory contains machines built by other machines. Every product passes through dozens or hundreds of production steps. Each step requires machinery. That machinery was built by other machinery. The cascade extends backward through time. Modern CNC machines were built by computer-controlled tools. Those tools were built by semi-automated machines. Those machines were descendants of the machines Keller designed. The engineering lineage is unbroken. The principle remains unchanged. Industrial capacity is built recursively, one generation of machines building the next. The engineers who designed this system received little recognition. Their machines weren't glamorous. Their work wasn't secret, but it wasn't publicized. They toiled in anonymity while pilots became heroes. But their contribution was foundational. Without machine tools, there are no aircraft for pilots to fly. Without machine-building machines, there are insufficient machine tools. Without engineers willing to design for reproducibility over perfection, the entire system fails. Keller's team understood this. They accepted that their machines would be crude. They accepted that their contributions would be invisible. They designed for impact, not recognition. In a memo dated November 1942, Keller wrote to his team, "Our machines will never be admired for their elegance, but they will be appreciated for their utility. We are not building art. We are building capacity. Capacity is built through repetition, not perfection. Remember this when you're tempted to over-engineer." That memo captured the philosophy that won the war. Good enough, built in quantity, deployed immediately. Better than perfect, built in small numbers, deployed eventually. The machines that built machines were good enough. They were built in sufficient quantity. They were deployed immediately. They won the war. Nobody noticed. That's exactly as the engineers intended. The invisible victory is still the most important victory. Tools before products, capacity before output, reproducibility before optimization. These principles built the arsenal of democracy. These principles won World War II. These principles will determine who wins the next industrial competition. The machines that build machines are the foundation of everything else. They always have been. They always will be. And the engineers who design them will remain in the shadows, building capacity, enabling production, winning wars invisibly, one machine at a time, building another machine. That builds another machine. Forever. 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 Forever.